Trigonometric identities are very much like puzzles. So if someone gave you a really difficult puzzle and you solved it, you would be like, oh my God, I am a genius. But then there are those times where you don't solve them, and that's where you go around and round in circles, and then you feel very frustrated. I don't really want that to happen to you, so why don't I give you some background information and some tips as to how to solve these types of problems. Then you'll have more of the genius moments. Okay, so in the top left corner, you have a triangle, and the base is x. That's because it's along the x-axis. You have a height of y, and again, that's because it's vertical, like the y-axis. And then you have this line, your hypotenuse, which is like your terminal arm, and it spins around in a circle and is basically your radius. So if I'm looking from the perspective of theta, here's my opposite, my hypotenuse, and my adjacent. Now that I have all those sides, I can set up the 3 primary trig ratios and the 3 reciprocal trig ratios. Okay, so let's set up the 3 primaries first. Opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. Now the flips of those. Okay? What I'm going to do is I'm going to use those to prove 2 identities. So I'm going to create 2 rules. The quotient identity is called that because it's a quotient. You have sine divided by cos. And since I know what sine is, I'm going to put that in right now. That's y over r. I also know what cos is. That is x over r. And now what I'm going to do is I'm just going to simplify it. So you have y over r, and it's being divided by x over r. Now to deal with that, we're going to flip the second fraction and then multiply. You're starting to notice that, well, maybe you can cancel out your r's and you're left with y over x. I look at this and think, well, that looks very familiar. That's just tan. Tan is y over x. So this equals to tan theta. And that's the basis for this quotient identity. Sine theta over cos theta is equal to tan theta. So anytime you see sine over cos, you can always replace it with tan. Or the other way around. If you ever see a tan, you can replace it with the sine over cos, and that's actually the one that happens most. Anytime you see tan, you want to break it down into these fundamentals, the sines and the coses. Okay, the Pythagorean identity. When you see sine squared theta, that actually just means sine theta times itself. We don't write it like this, because then it looks like just the theta is being squared, when in fact you want the entire thing being squared. So they put the square in between the sine and the theta. But you know that it means your sine, which is y over r, just squared, plus your cos, x over r, and that's being squared as well. So that's going to give you y squared over r squared plus x squared over r squared, and notice that you can add them together because your denominators are the same. So we're just going to put them over the exact same denominator. There we go. I can actually go further because I'm noticing there's something interesting about this part right here. I'm going to scroll up a little bit. If you have x squared plus y squared, isn't that just the Pythagorean theorem? That gives you your r squared. In other words, I could change this to r squared. So when I do that, I'm going to get equals r squared over r squared, which is just 1. This identity, the Pythagorean identity, is sine squared theta plus cos squared theta is equal to 1. Now what you could do is you could always manipulate this identity a little bit. In other words, I could always go sine squared theta equals 2, and then bring this over to the other side. 1 minus cos squared theta. So anytime in some sort of an identity that you're trying to prove, and you see sine squared theta, you can replace it with 1 minus cos squared theta. Or, if you see cos squared theta in an identity, you could always replace it with 1 minus sine squared theta. So I gave you a lot of background information. Let's check out an example. So here's an example. They want you to prove that cos theta times tan theta over sine theta is equal to 1. This equals to will go in the middle of your left-hand side and your right-hand side. So all this stuff is your left-hand side, and that's why I wrote it here. All this is your right-hand side, and that's why I wrote it right there. Now notice that I did not write an equal sign in the middle of them, right here, because you didn't technically prove anything yet. You don't know that they're equal, so we can't really say that. Let's prove it first, and then we can say it at the end. Take a look at the right-hand side. It's only 1. There's nothing you can really do to it. It's very simple looking already. Let's take a look at the other side then and start working on the other side. Now the tan is one of my identities. Remember that for the quotient identity, tan is equal to this, which means anytime I see a tan, let's just replace it right away with a sine theta over cos theta. Then I'm going to write the rest. Cos theta is multiplying this, because that was a multiply, all over sine theta. Now, since I went from this step to this step, don't forget your equal signs, because that's going to be the exact same for the next step. Okay, so there's a 1 underneath the cos theta, and then when I multiply, those two cancel out. So as my numerator, I get sine theta over 1. As my denominator, I still have the sine theta. And notice that they're exactly the same, which means I can cancel them out, and I get 1. Now that looks a lot like the other side, which makes me happy because they balance. Both sides are the same. Therefore, you've proven that left side is equal to right side. Don't forget to write that, because you've done all the work. You may as well tell people, hey, I've proven that both the sides are the same. Let's try a trickier one. Here's my equal sign. So I put that right here. Okay, this is my left-hand side, and I've written it right there. And then this is my right-hand side. So I've written it right here. They haven't used thetas this time. They've used x's for their angles instead, and that's okay. We'll just have to do what they do. The left-hand side looks very simple already, so I'm going to start writing on the right-hand side. Remember that the tan x can be replaced by sine x over cos x, and that was being multiplied by sine x. Then there was also the 1 over cos x and the minus, and don't forget your equal sign, because again, this step equals to the next step, which equals to the next step. Now there's a 1 under here, which means that when I multiply the fractions, I'm going to get sine times sine, which is sine squared x. 1 times cos, which is just cos. And then to subtract them, they have the same denominator, so why not just write them underneath as 1 cos. Okay. Now it looks like we can't really go any further, and it doesn't quite look like the other side, but I'm starting to notice, well, didn't we say this was an identity right there? I can replace it with something. So going back to my identities, oh, here it is. Isn't this what I want to replace? And I can replace it with a cos squared. Okay. So why not replace this with cos squared theta instead? It's going to get a cos squared theta. Oh, not a theta. We're dealing with x's. over cos x. And if you have cos squared on the top, so that's a cos times a cos, divided by 1 cos, we're going to be left with 1 cos on the top. And that does look a lot like that. Okay, so we've proven that both sides are the same. They're equal. Therefore, left side equals right side.